Welcome. I just wanted to make a little video here to prove this theorem concerning the sum of subspaces and their dimension. And so let's get to it. If V is a vector space over a field, and we have finite dimensional subspaces U and W, then U plus W is also finite dimensional, and the dimension of U plus W we can prove it's equal to the dimension of U plus the dimension of W minus the dimension of U intersect W. Alright? So let's see how this is proved. So the first thing I need to establish is that U plus W is in fact finite dimensional. Now the argument for that goes like this. Since the dimension of U and the dimension of W are both finite, that means we can find finite spanning sets S1 and S2, and it's easy to verify that the union of two such spanning sets is also a spanning set for U plus W, which is defined as such. Now, I haven't actually proved that here, but that would make an easy homework exercise, alright? But notice then that the number of things in S1 union S2 is the number of things in S1 plus the number of things in S2. So here I'm not doing that usual thing we do with sets where I'm saying if we have a repeated element in S1 and S2 that we only count it once. Like this is, technically this is working with what's called a multi-set where we allow for duplicated elements if I say the counting works like that. But anyway, you can do that if you want, and I do want to do that here. But the point is that certainly that the union of two finite sets is again finite. That's all I'm saying. And if that's true, then we can select a finite subset from the union, which serves as a basis for U plus W, right? By removing vectors from this until it becomes linearly independent, using the plus-minus theorem we talked about the other day. So anyway, that goes to show you that U plus W is in fact finite dimensional. All right. Now this whole proof could be avoided if we simply supposed that V was finite dimensional. Let's see, if V was finite dimensional, then it would be automatic that a subspace like U plus W is also finite dimensional, because you can't have an infinite dimensional subset of a finite dimensional vector space, right? But I didn't want to do that because I wanted this theorem to still hold if V was infinite dimensional, and we're just talking about finite dimensional subspaces of a infinite dimensional space. Okay, so move on then. So the next part of the proof, let's see here, move this, scooch this up here a bit, there we go, is to notice that we're given, U and the subset of V, and W a subset of V, rather subspace. Well, we can also prove that the intersection of subspaces is a subspace, and we can also show that U plus W is a subspace as well. And more than that, the intersection is contained inside U, which is contained inside U plus W, and likewise the intersection is contained within W, which is contained within U plus W. Alright, so these things are true. So now we're starting to get to the meat of the proof, if you will. We're going to suppose that there's a basis for the intersection subspace, which we're going to enumerate 1 through n, with V's, V1 through Vn. It's a basis for the intersection. And then, since the intersection of U, since that's a linearly independent subset of U, we can complete it to a basis for beta U, which we will denote by adjoining U1 through UD. Alright? So in this context, the dimension of U is n plus d. Alright. And we can likewise extend the basis for the intersection to a basis for W, alright, by adjoining W1 through WE to the existing V1 through Vn. So apparently the dimension of W is also n plus e, alright. Now, this line down here, I don't think I ever actually needed to use, but it's true that the U1s through UDs, they're in U, but they're not in the intersection. And the W1 through WEs, they're in W, but they're not in the intersection by construction. And that does kind of guide the practical application of this theorem to a specific construction. We'll look at an example at the end of this video. But let's finish the proof here to start with. And so great. So here's the deal. We Next, define. This is a definition, all right? So I'm just defining the set. I'm just defining the set beta u plus w, and by simply adjoining the v's, the u's, and the w's that we previously constructed, all right? And then, in fact, we can claim that beta u plus w is aptly labeled, is in fact a basis for u plus w. And if that's the case, then the dimension of u plus w is the number of things in here, which is n plus d plus e, which we can rewrite as n plus d plus n plus e minus n, which shows you then the desired claim that the dimension of u plus w is dimension of u plus dimension of w minus the dimension of the intersection. Yay! So it remains, of course, then to show that that is in fact a basis. All right? So let's look at that. Now, so first we'll show it's a spanning set. So pick z in the sum of u and w. That means that there exists x in u and y in w such that z is x plus y. But remember, x is the span of beta sub u, which means x can be written as sum of the v's and the u's for appropriate constants in the field. And y is an element of the span of beta sub w, which means that y can be written as a sum of, well, v's and w's for appropriate choices of scalars alpha and beta. All right? Thus, if you put that all together, we have this, and, sorry, I need to make a slight editorial correction here. There's an errant parenthesis that got away from me. There we go. All right, fixed. Now, continuing here, you can regroup those first two sum, like this sum and that sum, right? Those go to here. Since I'm at this, let me add some color coding. This guy and this guy, we can put those together, and they give you this fellow right here, right? And the other two sums just sit there. But you see what you got? You got something that's a sum of v's, u's, and w's, which is exactly the content of beta u plus w, v's, u's, and w's, all right? Therefore, beta u plus w, it can form x plus y, which is an arbitrary element of the sum, as a linear combination. Therefore, it's in the span of beta u plus w. Quiet over there. Anyway, so that's a spanning set, yay. So it remains to show that beta u plus w is in fact linearly independent. All right, so let's do that. So, here we go. Get things in order. So how do you show something's linearly independent? Well, usually, the right thing to do is to take an arbitrary linear combination of said things, set it equal to 0, and show that this implies that the coefficients are all 0. This is more often than not the correct thing to try to do to show a given set in linear algebra is linearly independent. Because in linear algebra proper, we can't just do row reduction of some matrix because we don't have a matrix, right? Anyway, off soapbox, back onto proof. All right, so here, observe x is a linear combination of the u's, since it's in u, and y is a linear combination of w's, and that makes it in w. Of course, we already knew that x and y were respectively in. I'm sorry, this x and y is no relation to the previous x and y. Maybe I should put like bars on these or something so that we're not tempted to think these are the same x and y early in the proof. I'm gonna slap some bars here. There we go. Now they're different. X bar and y bar. All right, great. Now, thus y bar is equal to that minus x bar, right? So it's the difference of this and that. Now notice that the v's are in the intersection. Well, I mean, this is just algebra at the moment. But my next comment is that this thing is in the intersection of u and w. Man, I don't have a black. Rats. That's a w. So, and on the other hand, of course, which is a subset of u, but it's also that x is in u, so it's a difference of things in u, therefore y bar, therefore x bar is in u, So the difference of things in U is in U because U is a subspace. Consequently, y bar is in U. Therefore, y bar is in the intersection of U and W, because we've argued that y bar is an element of W, but it's also can be written this way, and that's an element of U as well. So since it's both in U and W, it's in the intersection. But hey, we know that there's a basis for the intersection of U and W by our starting construction, and as such, we have, if I can put the bars everywhere, there exist scalars a to 1 through a to n, such that the sum of those scalars can construct y, but y is also given by this, right, by construction. And of course all of that rests on the star equation that I had up at the top there. And so, hey, but this is a linear combination equal to another linear combination with respect to the basis. Now we can look at this as a linear combination, not with respect to the intersection basis, but by the U basis. See, remember the beta U basis is formed with the V's and the U's. So looking at this, we can equate coefficients using the linear independence of beta sub U, and that tells us that the eta sub I is equal to minus alpha sub I. Okay, great, not particularly interesting. But it also tells us the much more exciting fact that beta sub j is equal to 0, because there is no u sub j over here. So equating coefficients of the u sub j's, we get that beta sub j is equal to 0. I guess to be fussy, we get minus beta sub j is equal to 0, right? But it immediately follows that beta sub j is equal to 0. And then, putting that back up into equation 1, gives us this. It's just the, okay, we're not using, fine, not equation 1, but I should really say star. We're going back to star again, okay? So, going back to star once more, since the beta j's are 0, it just leaves us with that and that, which gives us that this linear combination is 0, but hey, that's a linear combination in the beta w basis, see, because remember the w basis is formed with the v's and the w's. So this is a linear combination of elements of beta sub w equal to 0, which by linear independence of the beta w basis gives us 0 coefficients, alphas and gammas, all zeros. Hence, we have shown that the coefficients of the original linear combination here are all 0, which proves the linear independence of beta of u plus w. Indeed, we have shown that beta u plus w, so defined, is in fact a linearly independent spanning set, which is to say it's a basis, and we're done with that. So now I thought it would be healthy for us to see an example, just to sort of show you a token example of how these things play out. All right. So here I take, you could put this example in the larger context of like polynomial space if you wanted, but I decided to just be lazy and do a finite dimensional example, so my bad. All right, so here we go. You've got u is this, so I'm saying set of cubic polynomials with 1 and 2 being sent to 0, set of cubic polynomials that go through x equals 1 and x equals to 3 on its graph on the x-axis, right? So of course the intersection is going to have all of the conditions met, so 1, 2, and 3 are all sent to 0. And that's easy enough to see exactly what that is. By the factor theorem, I've got a times x minus 1 times x minus 2 times x minus 3. Lo and behold, that's the span of that. This is clearly a non-zero vector, therefore the dimension of the intersection is 1. All right, there's step number 1. Step number 2 here, I want to look at u. Well, by the factor theorem, u is simply this, because it's, 1 and 2 have to go to 0, so by factor theorem I can factor those out. Since we're a subset of P3, it has to be cubic, so that leaves you ax plus b out there. And so, this is then giving us the span of x times x minus 1 and 1 times x minus 1 times x minus 2. There you go. These are clearly not multiples of one another, because x is not a scalar. And therefore the dimension of u is 2. Woohoo! And not surprisingly, the dimension of w is also 2 by a very similar calculation, this time based on factoring out x minus 1 and x minus 3. All right. So then, what does that say about the sum? Well, the sum of u and w, right? How big is it? Well, the dimension of u plus w is dimension u plus dimension w minus the dimension of the intersection, which in this context is 2 plus 2 minus 1, 3. So apparently, u plus w is a three-dimensional subspace of cubic polynomials. And if you think about that, we notice that it's f of x plus g of x, where f of x is in u, g of x is in w, right? Okay, so that if we, here's the, this is kind of a jump, but this jump is supported by what's in red, all right? Not much of a jump, really, but, okay, so you have f of 2 is 0, and f of 3 is 0. I mean, g of 3 is 0. Okay, great. That doesn't really tell us anything about f plus g of 2 or 3, because the other one, the remaining one, which isn't 0, is arbitrary, right? But they do share the common f of 1 being 0. So if I call h equal to f of x plus g of x, then like f of 1 plus g of 1 is h of 1, which would be 0. So we can rightly cipher that u plus w is in fact the set of polynomials in P3 such that h of 1 is 0. But of course that is simply a quadratic, right? That we can factor out a quadratic, and by the factor theorem we have, x minus 1 times that. So a basis for u plus w is x squared times x minus 1, x times x minus 1, and x minus 1. Indeed, the dimension of u plus w is 3, since these are linearly independent, I claim. Okay, so if this was a standalone calculation, maybe I owe you a proof that these are linearly independent or something. But I don't need that. I can be more certain of this slightly sketchy calculation because I have the dimension theorem to guide me. So here's a slightly less sketchy calculation for, oh man. Well, I guess that's where we're going to have to stop because I've lost my other paper. Oh well, so sad. Too bad. Anyway, have a great day, guys. Thanks.